Welcome back for lesson 4-3, day 2. So we're going to be doing more graphing today using transformations of the absolute value function. So you're going to need the day 2 note sheet along with something to write with. So here we go. All right, so recall that we have the absolute value function as the absolute value of x. And remember, the parent function is the most basic form of that particular type. So when we just have a plain x there. So remember, when we start putting numbers into the function, that's when things start to shift on the graph and to move it up, down, and left or right. All right. So in the first video, we talked about vertical and horizontal shifts. So that's what I kind of just said, the left and right shifts and the up and down shifts. So today, what we're going to be talking about is what happens when we start putting coefficients in front of our problems. So if we have a number in front of the absolute value, okay? So we're calling that our A term. All right. So what we're going to look at today is what happens and how we get a reflection on the graph. And that's when the graph is going to do a flip. Okay, so instead of opening up like a V, it's going to open down. So a reflection, a lot of times we're just going to call it a flip, but we'll look at that. And then we're going to look at stretches and shrinks. Stretches are going to make the graph more narrow, meaning skinnier. And anytime we have a vertical shrink, that's going to make our graph look more wide. Okay. So let's just recall that the parent function always starts at the origin, 0, 0. And all of these graphs have that V shape to them. Okay. So now let's look at what happens when we change that coefficient in front. So I'm just going to write the general form here so we can talk about it. So what we're talking about today is what happens when I change this A value. Okay. So A makes the graph skinnier, wider, or it's going to flip it. Okay. So whatever number's in front of there, that's how that affects the graph. So anytime we have a number bigger than 1 as a coefficient, so anytime that A value is larger than 1, there is a vertical stretch. So if I had that V shape and I kind of stretched it, pulled it kind of up and down, okay, by stretching it, it's going to make the graph more narrow. Okay, it's going to make that V shape kind of really skinny. Okay, anytime we have a number that's kind of a fraction or a decimal, so something bigger than 0 but less than 1, so some kind of fraction like a half or 0.2, okay, that's when we're going to have a vertical shrink. So think about if I took that V-shaped graph and I kind of smushed it from the top, so I shrunk it, made it smaller. Okay, that's going to make the graph look more wide, so it's going to be a little bit more spread out. Okay, compared to the parent function. Okay, and then the last one, if anytime we have a value that's less than 0, meaning if you get a negative in front, anytime that a value is a negative, then there is a reflection on the graph, which will make the graph flip upside down, okay? Meaning the vertex then is at the top and that V shape is going to open downwards. Okay, so that's what we're going to look at today. What happens when we change the A, or that leading term, in front of the absolute value. So let's look at these examples. Okay, so in A, we have y equals 2 times the absolute value of x. Now, if I look at this 2 in front, 2 is bigger than 1, right? So this is a stretch. Okay, so this is going to make the graph more narrow by a factor of 2. So you can just say it's more narrow, okay? You could call it a stretch, but a lot of times I just say that the graph's narrow. I don't really refer to it as stretch and shrink too often, okay? All right, let's look at B. In B, we have a 1/3 in front. So again, anytime you have a fraction or a decimal, that's going to shrink your graph or make it more wide. okay, by a factor of a third. And again, or we can call this a shrink. Either way, I would take your answer. If you wrote wide or if you write shrink, it's the same thing. Okay? So now let's look at C. C, we have -3 times the absolute value of x. So we're going to take this one part at a time. If we have a negative in front, what does that do to the graph? Okay, a negative in front is going to make that become a reflection, meaning that graph is going to flip. Okay, so a negative flips the graph, and a coefficient of 3 is going to make it narrow, okay, or aka a stretch. Okay, so that's how we go ahead and deal with those. Now, if we have a graph, okay, remember the parent function also starts at 0, 0, but it has a kind of an increase of 1 over 1 on each side. So if I compare that to this graph, you can see that it's much skinnier, okay? It's much more narrow. And how you tell what factor it's being multiplied by, it's kind of like by the slope on each side. So for the parent function, it goes up and over 1, okay? So you can kind of tell that this graph didn't go up by 1. It went up 1, 2, 3 on each side. So that's how we know it's multiplied by a factor of 3. So they stretch that graph. So that's what I mean. If I were to grab hold of these endpoints and pull them upwards, that's what it means to stretch them. So it's going to make that V shape a lot more narrow. Okay? All right, let's look at E. So E is the graph, and we can kind of visually tell what's happening. But again, if this was the parent function, oops, I should do it this way. My parent function starts at the origin and opens up by a factor of 1 on each side. So like this. So if we compare that to the graph that was drawn for us on E, this graph is definitely more wide. Okay. And we can see that it went out by a factor. So how wide out did it go? It went out by 4. So this probably went, so you can see that it only goes up by a little bit, but this is wide by a factor of 1/4. Okay. Also, what happened to the graph? It's pointing downwards. That would give my graph a flip. Okay, so the transformations here, the graph flipped because it's opening downwards now, and it's also much wider, and it's wider by a factor of 1/4. Okay, and again, the way I get these numbers, the factors that they're wide or narrow by, is I just count by the graph. Where's my next point at? Okay, remember, if a graph is wide, it's going to be multiplied by a fraction or a decimal. If a graph is narrow, it's multiplied by a number bigger than 1. So now let's apply this to a graph. So we have the graph of y equals -4 absolute value of x. So we have 2 transformations happening here. Okay, we have a flip because of that negative in front. Okay, and then I also have a graph that is more narrow by a factor of 4. So there's no left or right shifts or anything like that, so I don't have to worry about doing any moving. So I'm still at the origin, but I'm going to flip the graph, meaning it's going to open down. And I'm also going to make it narrow or skinnier. So I'm going to multiply my next point by going up 4 on each side, like this. So again, the parent function goes over 1 and up 1, like this. So if I'm going to stretch it and make it more narrow, instead of going up and over 1, it's over 1 and up 1/4 from our origin spot. And then the flip just means it opens down. All right, next page, we're going to put everything together now. So remember, the A value in front is going to either stretch it, shrink it, or make it a reflection. Okay. The inside the absolute value is what moves our graph left or right. So remember, a plus moves it left, a minus moves it right. And then the plus k, the value outside the absolute value, that's going to move our graph up or down. So remember, a plus moves it up, a minus moves it down. So let's identify these transformations. So in A, we have y equals negative absolute value of x plus 3. So anytime we change the graph from the parent function, something happens to the graph. So I see two changes here. I see a negative in front, and I see a plus 3 inside the absolute value. So that tells me that the negative is going to give me a reflection, okay, or it's going to flip the graph. Again, I would take either word. If you said reflection or flip, that's fine. Okay, and then the plus 3, since it's inside the absolute value, a plus moves it to the left. So this graph goes left 3. All right. So I'm going to have you guys try B. So B has 2 times the absolute value of x minus 5. So I'm going to tell you there's 2 transformations there because there's 2 numbers in the problem. So list those 2 transformations. What are they? Okay. So the first one is it goes down 5, and that's because of this negative 5 here. Okay, so that means the graph goes down 5. And then that 2 is going to make the graph more narrow. So narrow by a factor of 2. All right, the last one let's do together because there's a lot to it. So I see a negative. I see a 1/2 in front. I see a minus 4 inside the absolute value symbol. And I see a plus 7 outside the absolute value symbol. So we have 1, 2, 3, 4 transformations here. So what does the negative do? The negative is going to give us a flip. It's going to reflect the graph over. What does the 1/2 do? The 1/2 makes the graph more wide by a factor of a half. The minus 4 inside the absolute value, minus moves it to the right. So it's going to go right 4. And then a plus 7 outside the absolute value, a plus moves it up. So we're going to go up 7. Okay. So again, anytime we put a number in the problem or any kind of symbol, it's going to transform our equation. So it's going to give you a transformation. All right, let's go backwards here. We have to write the equation given the transformation. So again, let me kind of rewrite our general form here so we can reference it. Or it's at the top of your page too. I just can't see the top of my page right now. So if we have a reflection, that means we have a negative in front. Okay. And then if we go left 6, remember left means we have a plus 6, and it's inside the absolute value bars. So now let's put that together with the equation. We have a negative in front. We have a plus 6 inside the absolute value bars. And that's it. Okay. Let's look at B, a vertical shrink of a half. Okay, so we have a half in front. And then we know we're going to go down 2. So again, down implies that it's a minus 2. And then remember, up and down is outside your absolute value. Okay, so now if I write this, a shrink means we have a coefficient in front. So 1/4, the absolute value of x, and then down 2, minus 2 on the outside. Okay, so I'm going to have you guys try C on your own, where you have a vertical stretch of 2, you have a reflection, and you also are going to go right 7. So how would you write that absolute value equation with those 3 transformations? Okay, hopefully you had something that looks like this. So a vertical stretch of 2 means you have a 2 for a coefficient. Okay, a reflection means you have a negative in front. And right 7 means you're going to have a minus 7 inside the absolute value. All right, let's look at D. So this one's got a lot going on. We're going to go down 9. We're going to go right 2. We're going to have a reflection, so a minus in front. And we also have a vertical stretch of 5. So that means I know 5 is going to go in front of my absolute value. Okay. Anytime we have a shrink or stretch, that's your coefficient. That's what goes in front. So here's my equation. We know 5 goes in front because that's our coefficient, our stretch. We have a reflection, so I'm going to put a minus in front. Down 9 means we have a minus 9 on the outside. Right 2 means we have a minus 2 on the inside. Okay? Maybe I should keep this color-coded like I had it on the problem. So there's our 1, 2, 3, 4 different transformations. So we should have 1, 2, 3, 4 numbers in the problem, which we do. Okay, so grand finale here, we're going to graph some equations. So there's some kind of steps here that can help you a little bit. So we always want to identify your transformations first. Plot the vertex. Remember, it always starts at 0, 0. You're going to start at the origin and then do your transformation from there, left, right, up, or down. And then anytime we have a stretch or a shrink, that's what they're talking about here, where we plot the slope. Okay. And then anytime we have a reflection, that means we're just going to flip it. So here we go. Let's look at A. So A, I have 3 times the absolute value of x plus 2. So we have a 3 in front. That tells me that this graph is going to be narrow. We're going to stretch it by a factor of 3. And then I also see a plus 2 on the inside. So plus tells me that it's going left. So we're going to go left 2 units. And that's the only changes to my parent function. So that's my only 2 transformations. So remember, the parent function starts at the origin. So I'm going to take this graph. I'm going to shift it left 2. And now we just have to plot the points to make it narrow. So remember, if it's narrow by a factor of 3, that means on either side of my vertex, I'm going to go up 3 units. And that should make our graph narrow. And there we go. Okay. All right, so let's look at B then. Again, I have 2 things going on. I see a 1/2 in front. So anytime we have a fraction in front, it's going to make the graph more wide. So we're going to go wider by a half. And then I also see that this graph has a minus 5 on the outside. So outside means it's going to go down 5 units since it's minus 5. Okay. So again, if I mark my parent function start, it's going to be at 0, 0. So my only shift I have to make is down 5. So here's my new vertex. And then we just have to widen this graph by a half. So similarly, like what I did on A, I went over 1 and up 3 because it was narrow. Do the same thing. Go over 1, but just up a half. And there's your graph. So if you connect those dots, you can tell that that's going to make the graph wider. Okay, it shrinks it. Now, when we're actually doing these on assessments, the only point I'm actually going to care about is your vertex point. As long as that point's in the right spot and you draw your V shape, which should be good. Now, if it's supposed to be wider, I want you to visibly draw it wide. Okay, if it's supposed to be narrow, draw it narrow. Okay, but there you go. So you guys are going to try the last one. This has a negative, a 2 in front, a minus 1 inside the absolute value, and a plus 1 outside. So you have 4 transformations there. So try to figure out what are all 4. Start with that. And then graph it by shifting your point from the origin and then taking care of any shrinks, stretches, or reflections. So give it a try here. So take a pause and go ahead and try it. Okay, so the negative in front is going to flip the graph. The 2 in front is going to make it narrow. The minus 1 inside the graph is going to move it to the right. And then the plus 1 on the outside is going to move it up 1. So starting that graph off at the origin, like our parent function says, moving the graph right 1 and up 1 gives me my new vertex point. And then the only thing extra I have to do is make sure I flip it and make it narrow. So if it flips, that means it's going to open down instead. So if I make it narrow, I'm just going to go over and down 2 on the sides of my V. So your graph should have looked like this. Okay. So now you guys have seen how to transform any function of absolute value, okay, based on that parent function. So look back up at this top. This is kind of our key spot here where it gives you all the different kinds of transformations you could have. So again, anything in front is going to stretch it, shrink it, or give you a reflection. The reflection comes from a negative. If there's a number inside the absolute value bar, that's going left or right. Anything outside the absolute value would move it up or down. Okay? All right, that's the end of activity 4-3.